Good evening, fellow night owls. This is Dr. Nighttime, and I'd like to walk you through how to use a particular result from engineering circles, of all places, in order to solve some probability problems. So let's start with a standard problem. That's the sort of thing that will come up on Exam P. Suppose a car insurance company has written policies for 1 million drivers. The policy only pays for damages from the first crash of the year and has a deductible of $500. It is estimated that, on average, only 10% of drivers will crash in a year. If a crash occurs, the damages will be exponentially distributed with mean $1,000. The company wants to have some amount of money X set aside such that they are 95% certain that the money will exceed the coming year's claims. How much should X be? Alright, so the first thing we notice is with such a large number of presumably independent behavior drivers or independently behaved drivers, we can invoke central limit theorem. It allows us to set up this 95% confidence interval by just finding the mean and standard deviation of the payments, or the combined payments from these million drivers all put together. That's called the aggregate loss, or the aggregate payment. All right. And we have formulas for that for exponential distributions, but not when it's this weird, well, it's exponential, except sometimes it's exactly 0, and sometimes it gets shifted over by 500 to force it to be exactly 0. So we need to do a bit of algebraic juggling for this. First thing we want to know is what's the probability of the company paying out exactly 0? Two ways that could happen. Maybe the driver didn't crash, right? We estimate that 10% will crash, which means 90% won't. So probability of not crashing is 90%. Then, what if you do crash, but the damages are between 0 and 500, and thus the company doesn't have to pay for any damages because it's within the deductible? All right, so there's a 10% chance of having a crash to begin with, and then if there's a crash, the probability of the damages being between 0 and 500, because it's an exponential distribution, is 1 minus e to the negative 500 over 1,000, where 500 is the cutoff and 1,000 is the mean, mean damage amount. If you aren't familiar with that formula, that's probably a sign that you haven't worked through enough practice problems associated with exponential distribution yet. I recommend that you just work through some more practice problems. You should have that formula memorized by accident. Anyway, so that probability that there is a crash, but that the damages are less than $500, that is 0.061, or 6.1%. So total probability that P payments equals 0, that's going to be 0.961, or 96.1%. So there's a 96.1% chance that you'll kind of be right here in this spike, or what I'll call a point mass, because I'm viewing it from an engineer's perspective. And so there's a 96.1% chance that your payment will be 0, and the remaining 3.9%, right, 100% minus 96.1%, 3.9% chance that the payment amount will be somewhere in this exponential range. And we know that if we shift over and truncate an exponential, we get another exponential with the same mean. It's a property of the exponential distribution being memoryless. So that gets us that the expected payment amount is going to be 96.1% of 0 plus 3.9% of 1,000. Grand total, $39. Okay, so we found the mean. Now we knew that the mean wasn't going to be the hard part. The harder part was going to be trying to figure out the variance of this, which the conventional way to do it is to just kind of use this formula up here. Yeah, that integral here, you're going to have to do integration by parts on that twice if you want to use conventional means to solve this. So if you really enjoy doing integration by parts twice and wouldn't want to use a shortcut, I mean, I'm no psychologist, so I can't diagnose you as a masochist, but well, for the rest of you who probably wouldn't want to have to go through that, here's how you can avoid it. So there's this neat little result here that lets you find the expectation of the square distance between some random variable x and any particular number a if you already know the square distance between x and its mean, mu. It's that this formula, expectation of x minus a squared equals expectation of x minus mu squared plus a minus mu squared. This is known as the parallel axis theorem. Feel free to look that up and find more resources on that. Comes up an awful lot in engineering. Surprisingly, I just haven't heard people talk about it much in the probability context, but to my mind they should. That's why I'm talking about it. So what happens when we use this formula? Well, we're really interested in the expectation of this random variable that could be here at 0, could be anywhere in this exponential range. If we set a equals 39, where 39 is the average value, so I kind of got that here at this blue dot. Didn't quite draw it to scale, but that blue dot represents 39. We want the expectation of the square of wherever x happens to be minus 39. So we'll say this expectation of x minus 39 squared that we want to know equals expectation of x minus its mean squared. Now, if we're only looking at values in the exponential range, then if we condition it on that, we're looking at these values within the exponential range. Well, so those values within the exponential range, we know that their square distance from their own mean of 1,000 is going to be 1,000 squared, because one of the properties of the exponential distribution is that its variance, that is square distance from its own mean, is equal to the square of its mean. So we know that this expectation of x minus 1,000 squared is just going to be 1,000 squared, or 1,000,000. Then, by parallel axis theorem, we have to add the square of the distance between this 39 here and this 1,000, which is going to represent, or it's meant to represent the average of just the exponential component. All right, so 1,000 squared plus 39 minus 1,000 squared. With the calculator, you find that that's 1,923,521. So if we want to look at the full distribution of these probabilities, there's a 3.9% chance that you're in this exponential range. So 3.9% chance that you're in some range where the expectation of payments minus 39 squared is going to be that 1.92 million. And a 96.1% chance that you're exactly at 0, and therefore your square distance from 39 is just 0 minus 39 squared, or 39 squared. So we just say it's 1.92 million times 0.039 plus 39 squared times 0.961. That turns out to be 76,479, and that ends up being variance of P, variance of your payments P. And yeah, we can kind of see the light at the end of the tunnel now. We just take the square root of that, and that gets us the standard deviation of a single payment, right? Because all this time we were just thinking about just one payment. So standard deviation square root of that, and that turns out to be $276. So we say that for one driver, the mean payment is $39, standard deviation is $276. For 1,000,000 independent payments, the mean is just 1,000,000 times the individual mean, $39 million. The standard deviation is going to be the standard deviation for one driver times the square root of the number of drivers. In this case, square root of 1,000,000 is 1,000. So sigma is going to be $276,000. And finally, the critical z-value for a one-sided 95% confidence interval is 1.645. And again, that's one of those figures that if you don't remember it yet, don't worry. Assuming you're practicing enough to pass exam P anyway, you'll have it memorized by the exam date. we say x, the total amount you need set aside, equals the mean plus 1.645 times the standard deviation. That's going to be 39 million plus 1.645 times 276,000, which gets us approximately $39,450,000. And so that's how much the company should have set aside. Notice that we were able to not mess with any of that scary looking integration by parts and solve this problem just using memorized properties of the exponential distribution, as well as the parallel axis theorem, which just allows us to do simple, relatively simple arithmetic, the difference of two numbers and their square, allowing us to greatly reduce the amount of work required to actually solve this, and thus reduce the probability of making an error somewhere, and increase the probability of actually getting it right. So I hope you found this useful. And until next time, this is Dr. Nighttime wishing you a good night.